Hello, everyone. I want to start this short presentation with a brief introduction on high-energy physics and the root project. Afterward, I will scratch the surface of HighEnergy, a project that will provide access to high-energy physics data for the upcoming years. Then I will give an overview on our new HighEnergy DAOS backend and our first evaluation. And finally, I will conclude the presentation with some closing words. High-energy physics studies the laws that govern the universe at the smallest scale, that is, fundamental particles and their interactions. Hence, the study of forces and their carriers must... Can you hear me well? Okay.
Yeah, can you hear you well? I will mute someone who is making noise, but
Okay,
you are good.
The force carriers, mass, etc., are also part of this area. All this is described in the so-called standard model. Here at CERN, experiments observe particle interactions. Typically, we do this by accelerating particles at high energies and use the detector to have insights on what's happening inside. In that scenario, particles decay in more fundamental particles that may interact. In this context, high energy physics data, or just HEP data, equals detector observations. The LHC, or Large Hadron Collider, is the largest accelerator at CERN. Basically, it's a 27 kilometers ring on which the four main experiments, ATLAS, CMS, ALICE, and LHCb, are located. LHC accelerates proton beams that move in opposite directions, that are forced to collide at specific points that are the detectors. And you can think of a detector as a 100 megapixel camera taking a picture every 25 nanoseconds. This is known as an event and can be graphically visualized as shown in this image. LHC produces 1 billion of collisions per second that lead to a huge data volume in the order of 10 terabytes per second. Thus, online processing limits to filtering as part of the detector readout. So most of the processing is done offline in a distributed manner throughout different LHC computing centers around the globe. In regards to offline analysis, the root project gives the foundation of high-energy physics data analysis. It provides C++ interpretation through the Clean C++ interpreter, object serialization, and I/O, as well as statistics, graphics, and much more. It's mainly written in C++ and features dynamic Python bindings through PyRoot. Focusing on root I/O, it permits the row-wise or column-wise storage of any C++ object. Typically, given high-energy physics analysis often requires access to a subset of the properties stored for each event. So here in the image on the right, you can see each of the data members of an event. Given that we are only using a subset of them for an analysis, row-wise storage is inefficient. Therefore, we have a T3 that organizes the dataset in columns that can contain any type of C++ object. That way, a number of instances of the same column of the same data are stored together. Currently, there is more than 1 exabyte of high-energy physics stored in T3 root files. Given that T3 has been there for 25 years already, HighEnergy is the R&D project to replace T3 for the next 30 years. And in that context, object stores are meant to be first-class citizens here. After this short introduction, I will scratch a little bit the surface of HighEnergy. This figure depicts the architecture of HighEnergy. The layer at the bottom, the storage layer, abstracts the details of specific storage systems and provides unified load store primitives to the upper layers. The primitives layer groups several instances of fundamental data types, for example, or that is a column, and it is conformed as or several values are grouped together into pages that may not be compressed. The logical layer maps C++ types into columns, and the event iteration layer provides convenient looping over events for reading and writing. In order to provide DAOS support, we are only going to focus on the storage layer. This figure shows the layout of an errand tuple file. It is comprised of an anchor, a header, and a footer, as well as a set of pages that are grouped in clusters. So to put it simple, a page can contain a group of values for a specific column and are in the order of the tens of kilobytes. And the header contains the information about the schema, and the footer in turn contains the location of pages and clusters. Lastly, the anchor specifies the offset and size of the header and footer sections. Looking at this layout, nothing prevents us from storing specific sections, for example, pages here, as objects in an object store. So at this point, I will give an overview of the new errand tuple DAOS backend. First, as errand tuple is C++, and to simplify libDAOS usage and resource management, we wrote C++ classes for part of the libDAOS functionality. This avoids boilerplate code for simple common tasks and provides our AII, resource management. In this example, this excerpt shows how the contents of a std string can be written to a DAOS object. Of course, this is a simple example, but we also provide support for more complex tasks. Returning to the errand tuple on disk file layout, we can map each of the entities as follows. Each errand tuple page is stored in a separate object, where the UUID is assigned sequentially starting from the UUID that has all the bytes to 0. And the header, footer, and anchor are stored in 3 different objects with reserved high-numbered UUIDs. From the user's perspective, switching from the file backend to the DAOS backend only requires to change the path to the file path and the end tuple name to a DAOS URI that comprises the pool UID, the service replicas, and also specifying the container UUID. As part of this presentation, I will provide the first evaluation results. Our evaluation ran on the CERN OpenLab DAOS testbed that was part of the previous presentation. This is comprised of 3 DAOS server and 1 DAOS head node that are interconnected by an omnipath edge switch. And these are the hardware specifications that can be found in these tables and that can be consulted later. First of all, the results in this section are preliminary and might not be relied upon completely. That said, before implementing the DAOS backend for errand tuple, we were aware of diffuse, the fuse file system that reads or writes to a DAOS system. Therefore, on our first stage, we used the errand tuple file backend in conjunction with diffuse. But before that, we performed some basic diffuse benchmarks that include sequential and random read-write for different block sizes. As can be seen in the table, the throughput for small block sizes is fairly low, and also writes are typically faster than reads. Note that all the numbers are in megabytes per second. And it's worth noting that in the best case, that it's block sizes of 4 megabytes, we are still 1 order of magnitude with respect to the theoretical limit that was measured by iPerf. This slide shows the runtime for 2 benchmark applications using OpenFabrics interface plus sockets transport. Both plots show times for 3 different scenarios: the local reading or writing a local file, reading or writing a file that is stored in diffuse, and our native errand tuple DAOS backend. On the plot on the left, gives an idea of the time that took to import existing data onto one errand tuple, that is the write performance. And the plot on the right corresponds to a benchmark that operates on LHCb data file and illustrates errant tuple read time. As can be seen in this scenario, our backend does not perform nicely for writing, as it is much slower than diffuse. But in the case for reading, we outperform diffuse. This slide shows the results for the same benchmark applications, but this time using the PSM2 protocol. As can be seen in this case, we outperform in both cases, the writing and the reading scenario, we outperform diffuse. So let me summarize the presentation with some concluding remarks. There is currently more than 1 exabyte of high-energy physics data stored in the root T3 files, and errant tuple will replace T3 columnar storage for the next 30 years. Also, errant tuple decouples storage from the actual data serialization or representation, and here is where object stores have a special importance. And therefore, we have implemented the first prototype for an Intel DAOS backend that it's integrated with errant tuple. Currently, we are mapping each page with a distinct object in the DAO system, and we are using constant distribution keys. This will not be the case in the future. We have just started our performance measurements, so they are currently not very reliable, and we have detected also some performance issues. So at this point, our next questions will be, first, how to maximize throughput so as to provide bulk reading of or writing of pages, and secondly, how to distribute pages appropriately. That is, put together pages corresponding to the same data member. And that is the end of my presentation. I hope to have been on time so that there is time for some questions or whatever.
Thank you a lot, Javier. Yeah, I think you are perfectly on time. Is there any question for Javier?
Well, one quick question maybe. Is there any use cases of, well, basically just on the general popularity of the root format? Is it used widely, or is it just a CERN project? Just maybe if you can comment on that, on how widely is it used?
Yeah, actually, the root format, I would say it's the ad hoc standard for storing high-energy physics data. It is used, I think, by more than 10,000 physicists around the world. And yeah, it's actually a de facto standard, I would say.
Great, thanks.
Okay, thanks a lot, and we will be happy to collaborate more on the performance improvement and the few items that you mentioned at the end.
Perfect, that would be really nice. Yeah.